All right. Well, thank you very much for joining us for our aerospace senior design presentation. You can see our names listed below there. This is a little bit of a Mark II design of our plane here. We can get into our project goals. So for the overall goals of our project, we were doing 3 laps in a 5-minute flight time as a minimum. So we wanted a relatively large wingspan. We went for around 5 feet or 1.5 meters. We wanted a relatively slow cruise speed of around 17.5 meters per second. We wanted stable flight. We'll get into a stability analysis a little bit later as well. We wanted an affordable plane in terms of manufacturing, as well as just like printing costs, any material costs, any things like that. And so we went with a lightweight PLA, which we'll also get into a little bit later. You can see a little bit of the course layout shown to scale there in the bottom right of the slide. And we will get into our maiden flights as well as the top right of the slide here. You can see our Mark II design of our plane.
So let's get into wing design. We started with airfoil selection, which was conducted in XFLR5, a CFD program specifically catered to fixed wing aircraft. So as you can see here, we compared 4 airfoils, a Clark C, 2 GOEs, and a SD7062. These were compared at a Reynolds number of 211,000, which is based on our estimated cruise velocity and our wingspan. These airfoils were compared for 3 characteristics: the lift slope, the efficiency, and stall characteristics. So as far as those go, the GOE 443 outperformed the other airfoils in lift slope and efficiency, but the SD7062 had a large advantage in stall characteristics, which is better for an inexperienced pilot because you don't want a plane to be stalling all of a sudden on a first prototype. So we can move on to our overall wing design. So the first 3 characteristics you see here are pre-selected for. So we first decided on a high wing because it offers more roll stability, which is better for an inexperienced pilot. We decided on a 5-foot wingspan around 1.5 meters because it's easier to see down the runway and also won't bring up manufacturing times too much. So it's a good middle ground. And we decided on a cruise speed of 17.5 meters per second. The other characteristics you see here, the aspect ratio, taper ratio, and incidence angle, were decided also through XFLR5 on a separate analysis, which we can get to now. So this is the XFLR5 analysis for our total wing design. What we're looking for here is what angle of attack our wing will produce the right amount of lift for. We were designing for around 8 pounds of lift at cruise velocity. And that happens at around an alpha of 3 degrees, an angle of attack of 3 degrees. And that almost lines up with our maximum efficiency, which occurs at approximately 2 degrees. So those things line up, which is ideal.
All right, moving on to aileron design. Our ailerons consist of 30% of our average chord and 40% of our span. Our ailerons are actuated via 9-gram metal gear servos, just like all of our control surfaces, and they pivot around a 3mm carbon fiber rod axle. And this allows for deflection angles of 30 degrees in both the positive and negative direction.
So now under our fuselage design, we had a few design priorities here. We wanted to be lightweight and strong enough to resist all of the bending and torsional loads during flight. So for this, we considered a circular cross-section, as it is more aerodynamically efficient and also is stronger in torsion. Our length we designed for ease of printing, so not too long. It can be printed in 4 sections. And there are semi-bulkheads throughout, so planar sections throughout the fuselage with holes in the middle for wiring. And the entire fuselage is variable thickness, so a different number of layers of lightweight PLA throughout, and just to reinforce the structurally vital areas.
So based on our initial estimations and project requirements, the 2 parameters that apply to the propulsion system are the estimated aircraft weight of 6 pounds and a minimum 5-minute flight time. To choose the battery, propeller, and motor combination, we needed to enforce some restrictions. Based on our research of other RC aircraft of similar scale, we chose to have a thrust to weight ratio of 1:1, meaning the goal is to make around 6 pounds of thrust. Also, to alleviate the stress of our pilot, we set a minimum flight time of 6.5 minutes to allow for taxiing and at least one full 5-minute flight attempt. Lastly, we chose a maximum propeller diameter of 17 inches to allow for some ground clearance during takeoff. In the image below, you can see all the components of the propulsion system, the battery that powers the motor, which spins the propeller, all while the ESC, or the electronic speed controller, controls how fast the motor spins. First, focusing on the thrust to weight metric, we narrowed down 32 propeller and motor combinations using online testing datasheets, again constrained to 6 pounds of thrust and a prop less than 17 inches in diameter. However, each of the pairings performed slightly different depending on the battery size. A larger battery increases flight time, but it also increases the weight of the system. So to optimize the list, we compared each option based on their flight time to weight, thrust to weight, and thrust to input power ratios. Here is an example graph of each possible combination with the battery sizes differentiated by color. In this case, we want a longer flight time for a given system weight. So we fit a curve to the data and focused on options that perform better than average, so above this dotted line. And this was done for the other two ratios from the last slide, and a final group was chosen. These final four performed better than average in all three optimization ratios. From here, each of the characteristics was normalized between the entries, and the final system in red was chosen. The images below also show that final system.
All right, moving on to the design of our landing gear, we decided to go with a strutted tail dragger with directional control. This allowed for ease of pilot control on taxiing. A strutted tail dragger was also easier, we thought, than a bowed tail dragger in terms of structural stability within our fuselage. However, you'll see in the Mark II design, we decided to try out a bowed landing gear. We had front wheels laying forward of the center of gravity. This was due to the plane rolling forward on takeoff, and this helped with that, as well as the wheels forward of the center of gravity help with tail wheel instability, as well as the plane's tail shifting during takeoff. We used 3-inch foam tires around a Delrin wheel. These are attached to pieces of sheet metal that were adhered to the plane using strips of basswood on the inside of the plane as well. The original design, again, opted for 2 separate struts attached to either side of the fuselage. This was for increased ease of manufacturing, as well as worried for structural integrity, but you'll see in the future that we actually changed that.
So now we were ready to look at the structural analysis of the wing, and we did so by calculating the bending moment at the root of the wing. So one assumption we made was that our wing produces an elliptical lift distribution, which in theory is the most efficient. Shown by the chart down below, we used a taper ratio to get our lift distribution as close as possible to elliptical. Another assumption we made was that the loading forces were calculated at the maximum operating conditions, because we want to make sure our wing holds up in the most harsh conditions of flight. Shown on the right side is the equation walkthrough for calculating our bending moment. And I won't get too in depth, but we started with the equation of an ellipse. We solved for the lift forces based on X location in the wingspan, integrate that once to get shear stress, and integrate once more to get the bending moment. So for actual maximum loading conditions, we had a velocity of 20 meters per second and an angle attack of 15 degrees. This is very close to stall, so we hope our pilot doesn't put the plane there, but in case it does, we want our wing to hold up. Using XLFR5, we have a lift force of 125 newtons. The weight of our plane was 26.7 newtons, and again, a wingspan of 5 feet. So using those equations on the previous slide, we have a load factor of 4.68, Y0, which is a force distribution of 104 newtons per meter, and most importantly, the moment at the root of 20.15 Newton meters. I also want to bring up the historical data. As you see, our load factor falls right in line with that utility, transport, even bomber aircraft, which are all meant to carry weight. This is important later on when we had to add weight during our test flights.
So now that we've calculated the maximum bending moment, we could then design a spar to go inside our 3D printed wing. First, we started with material selection. We used an Ashby chart to determine the best material for a specific strength. So as you can see, carbon fiber is the best material to maximize that ratio. So after that, we looked for different manufacturers for carbon fiber tubing. So we found a manufacturer who produced a tube with the cross section shown. We decided to go with two 2-foot sections in the wing, leaving 6 inches on each wingtip without spar, but we thought that would be okay since that's not the maximum stress location. Then finally, using the moment of inertia and stress formulas and the bending moment from previously, we were able to calculate the max stress within the spar of 544 megapascals, leaving a factor of safety of over 3. And then this is the CAD model of the wing. You can see where the spars insert into. It's the little square holes through all of the bulkheads in the wing. And at the root, there is a longer section that the spars insert to, made of ASA plastic. After our hand calculations, we then confirmed our results with finite element analysis. So we did 2 analysis, one at typical cruise condition and one at the absolute maximum operating conditions. Under cruise conditions, we saw a max deflection of 2.7 centimeters at the wingtip, and under the maximum conditions, we saw a deflection of 8 centimeters, which are both more than acceptable.
Okay, moving on to our tail configuration, we went with a conventional tail design. This is because it prioritizes weight reduction and ease of manufacturing. It also allows us to mount all of our actuators on or within the empennage, and it consisted with historical data. Conventional tails are very popular for aircrafts because of their effectiveness. One thing that we did decide to do is we offset our rudder from our horizontal stabilizer, and that was to eliminate rudder blanketing during spin recovery. Now, here's a render of our tail design. We used a NACA 15 airfoil at the root and NACA 12 at the tip. This resulted in and we had a aspect ratio of 5.2 on the horizontal and a aspect ratio of 1.5 on the vertical. One thing I do want to note is that this is the final design. We did have a couple of designs in the design process, and we will show that coming up. So this is our maiden test flight design. One thing that we ended up doing is we had a feeling that we were going to be a little tail heavy when manufacturing, so we experimented with a smaller vertical stabilizer, but ended up being uncomfortable with the scale of it, so we decided to extend it back to the original design using foam board. We originally intended for all of the servos to be housed within the empennage, but this relied on using the carbon fiber rod as an axle, and the carbon fiber rod ended up not having as much torsional rigidity as expected, so we decided to mount the elevator servos on the exterior of the empennage.
Moving on to static stability, we first use the equation shown to get an estimate of the surface areas needed for the horizontal and vertical tails. So using those, we could kind of guess and check and iterate till we got estimates for our stability derivatives that we liked. And once we got a good idea of the surface areas that we needed, we could plug them into XFLR5 with our airfoil, and we could then get our final stability derivatives. So for pitch, CM alpha, we got -0.5. Yaw, CN beta, we got 0.2. And for roll, CL beta, we got -0.037. These are all within the stable range. The pitch and roll derivatives need to be negative, and the yaw needs to be positive to be stable. And that's what XFLR5 showed.
All right, moving on to dynamic stability. You can see our plots of longitudinal and lateral stability on the right side of the slide here. So our dynamic stability analysis through XFLR5 showed that our aircraft was damped, which prevents oscillations of the aircraft, noting that we were dynamically stable. It is worth noting that we had a positive spiral mode lambda of 0.043, which shows that the spiral mode diverges, but very slowly, meaning it was easily correctable with pilot maneuvering, as well as a bit of an underdamped Dutch roll, which we'll get into a little bit on our maiden test flight, but was also easily correctable with pilot control. If you move forward, we have an initial CAD model of our plane just to give you an idea of what it looked like in our initial design.
With our initial design chosen, it was on to material consideration, and as with everything else in aerospace applications, materials are very important. The majority of our plane was made using lightweight PLA, which was due to its low density and ease of modification. Lightweight PLA is a modified PLA that allows for foaming, lowering the density by almost half, as well as allowing it to be easily cut into and modified. For the wing spars, because it would have a lot of energy to absorb during flight and landing, we chose ASA for its high toughness relative to PLA and PETG, the other materials available to us. The next material we used was sheet metal for our landing gear because it was flexible and strong, both of which you want in landing gear to absorb the impact upon landing. And we chose to go with aluminum rather than steel to save on weight while we're maintaining the same stiffness for relatively same geometry. The next material in our consideration was carbon fiber for its very high stiffness and low density. It was hard to prototype with, which is why we went with lightweight PLA. However, we still used it for the spar for our wing, as well as the axles for all of our control surfaces. And the last material we used was basswood. Basswood has a very high strength to weight ratio for other types of woods, and it was really easy to modify for rapid field repairs after our initial test flights. Moving on to manufacturing, most of our airplane was manufactured using 3D printing with our lightweight PLA material. The advantages to this are the complex geometries that are available, basically making anything that you can come up with in CAD, as well as the rapid prototyping, where it just takes a couple hours to print rather than a couple days to machine or manufacture otherwise. Some constraints to 3D printing ended up being the limited print volume and it being a bottom-up process. Due to the limited print volume, we couldn't print our fuselage or wing in one section. This sort of helped, allowing us to use semi-bulkheads as our base plate. But it would have been nice to have a full fuselage exactly as it was catted instead of having any imperfections with the assembly process. As a bottom-up process goes, the first layer is the most important as it adheres to our entire build plate for the entirety of the print. Therefore, as seen in the picture, we added a large enough brim to ensure that we had enough adhesion to the build plate throughout the entire print. Next, we used sheet metal fabrication. Sheet metal fabrication was used just for its low manufacturing time. It was fairly imprecise, however, due to sheet metal's nature, it's very bendable and was able to be rebent and reshaped post-manufacturing. And then lastly, for the carbon fiber, we chose to do a wet layup on top of our 3D print. This was to minimize material as well as time on the hot wire CNC and vacuum bagging. We chose to go with 2 layers of carbon fiber as well as epoxy to adhere them, and we just wrapped it up and let it sit overnight. The results were relatively similar to what we have seen in demos for the hot wire CNC and vacuum bagging, so we thought our print was acceptable.
Moving on to the assembly, we use two different attachment methods, removable and permanent. For the reason we used removable attachment methods is because of the ability to save some pieces if they weren't damaged during our maiden flight or a couple of test flights. We used mostly fasteners and sliding fits. Our wing was designed as a removable piece attached to the fuselage using a base plate and fasteners. However, due to the fact that the base plate was made out of lightweight PLA, the fasteners ripped right through it. So ultimately, our team had to permanently attach it to the fuselage using 5-minute epoxy. Our motor was also attached to the front with fasteners and the motor mount, and our landing gear was attached to the side of the fuselage with bolts and basswood acting as a washer. As for the sliding fits, is mostly for our control surfaces. A carbon fiber rod would run through and attach into the wing section and allowing it to be removable. For permanent, and we also had locating holes throughout the entire wing section, as Chris said, that allowed for the carbon fiber spar to run through, making sure that the wing was completely aligned. For permanent attachment methods, our design consisted mostly of using 5-minute epoxy. The benefit of this was that it allowed for some gaps to be filled up. If there's little gaps, so it's thicker. But the setting time for epoxy was around 15 to 20 minutes per piece. As shown in the picture, Alex is waiting for one of the wing sections to set. Throughout our test flights, when we had to make quick repairs, we found that CA glue worked much better, as it's quicker and a lot easier to use. Post-processing, a lot of the post-processing work was cutting axis hatches into the fuselage that allowed us to access the inside of the fuselage. An axis hatch on the side of the fuselage was cut to allow us to access the electrical components, and another axis hatch was cut at the top of the fuselage to allow us to access the battery. The adjusting of the sheet metal was also done post-processing, and this was to make sure that the plane had enough clearance in the front with the propeller and that it was level. Now moving on to the test flights.
During our test flights, we experienced relatively adverse conditions. We saw wind gusts of sustained up to 19 miles an hour and gusts up to 25. It was quite clear from the beginning that we had failed to accurately balance the plane. It was quite tail heavy. We only sustained relatively minor damages on crash landing. We landed about a half mile away due to the high winds and low controllability. This was partly due to the lack of exponential control. Exponential control is an ability to linearize control inputs that are relatively unlinear. This was due to our use of rotary servos. As I said before, rotary servos do not have a linear output towards the ends of their travel. The neutral position of their travel is much more sensitive. In order to fix this, we used embedded software in the transmitter to reduce the outputs by approximately 35 to 50% on all of our control surfaces. This exponential control was not used for our throttle control for ease of piloting. In order to fix the problems we experienced on our first test flight, we had to add a machined ballast to the nose of our aircraft to get the center of gravity underneath the center of pressure of our wing. And after this was done, a short takeoff and landing was attempted, in which we experienced a veering to the left due to improper rudder control and landed in the grass, experiencing high rolling friction, causing the nose of the plane to dive into the ground, causing it to snap off. This was due to the fact that the lightweight PLA was not meant to withstand these forces. On the same day of that second test flight, rapid field repairs were made with the basswood sheets and cyanoacrylate glue, and this was very successful in reattaching the nose of the plane to the aircraft. This lost about an inch of fuselage length, but allowed us to accurately place the CG. After this was done, we attempted to fly again with a hand launch method, given that our landing gear would not properly attach to the basswood sheets, given our lack of materials and lack of tools to process at the field. We ended up flying unbelievably controllably through an 8-lap and almost 9-minute flight time. This was surpassing the requirements by over 200%. And after trimming the aircraft, several low passes were attempted to get control of the landing process, and the plane was belly landed with no damage sustained.
So after the third test flight, we modified several components of our aircraft for the final plane. First, we redesigned our fuselage by extending the wing box and remaking it out of carbon fiber. In the two crashes we've had, the fuselage was the main component which was damaged, so we believed that a stronger fuselage would be beneficial. We extended the wing box to allow for a larger allowable range for placement of the wing. This gave us more room to position the quarter cord of the wing on or behind the center of gravity, which allowed us to significantly decrease the amount of ballast in the nose of the aircraft. When we did a full redesign of landing gear as well, as was shown to be another point of failure in our crashes. The landing gear was made from a single piece of sheet metal as opposed to being made from two separate struts like before, which improved the alignment and strength of the part. Making the landing gear out of one piece of sheet metal also allowed us to move the mounting location to a much more favorable position. The landing gear was mounted between the wing and fuselage on top of the plane, with the fasteners of the wing running through the landing gear plate securing it in place. The new landing gear design also had the front wheels placed further in front of the center of gravity. With our plane having a heavy ballast in the nose, this lessened the chance that the plane would fall forward and give more clearance to the propeller. The final improvements made were the larger vertical stabilizer and rudder. As Teo mentioned previously, we shrunk the rudder and vertical stabilizer for fears of being too tail heavy, and so we redesigned it in our final design.
After making these improvements, a fourth and fifth test flight were conducted, and again, we experienced relatively adverse conditions with up to 16-mile-an-hour gusts of wind and thunderstorms with light to heavy rains. Although we did push forward that day, it was noticed that upon looking into the high-speed footage, there was significant pilot error on the takeoff processes. After takeoff, the plane uncontrollably rolled to the left, rolling wing over wing after touching down. This was likely due to the elongated and prolonged use of elevator, a negative elevator to be specific, in which the plane likely stalled its left wing, causing it to roll. There are several other contributing factors that require further analysis and future processes. Both flights it resulted in identical crashes.
This project allowed us to put our knowledge cultivated through 4 years of undergraduate aerospace engineering to practice. We learned how important following design specifications and dimensions during manufacturing were to ensure a meaningful connection between original intent and final product. There were several instances where a greater discipline for following specifications would have reduced manufacturing times due to workarounds based on new dimensions. We also learned that copious communication is crucial when working towards a collective goal. When working on a complex project with different people working on separate subsystems, constant communication was vital to ensure a seamless design. Overall, we each learned valuable lessons which will be sure to further us in our aerospace careers. We would just like to take a moment to thank Professor Dong and our TA John, who supported us greatly throughout the semester and gave us much needed guidance.
Thank you very much for your time.
Thank you. Great job. I really enjoy your presentation. So let's ask Jacob's feedback first.
Sure. Great presentation, guys. Congrats on getting off the ground, by the way. That's huge. The other group didn't get off the ground last time. So can we go back to your goals? I think it's like the first slide. Great presentation, by the way. Yeah, so one of the goals that you guys set is for it to be affordable, but carbon is kind of like the most expensive material you can get. So I was just curious as why you went towards carbon as a material choice.
I can take that one. So during the prototyping process, the majority of the materials that we used were lightweight PLA. And in order to get extra credit for the assignment, the professor suggested that we use a carbon fiber aircraft. And in order to satisfy this requirement, we decided to go ahead and make our fuselage out of carbon. This was a choice made for the grade.
Okay. Yeah, it's totally fair. I'll ask more questions on carbon later. Can we go to the battery stuff? I thought the plot you guys did was really good, which yes, this plot is awesome. I was just wondering how you guys correlated battery size to flight time. How did you calculate that? Was that like a spec sheet thing, or did you calculate yourself?
Yes, we used a big Excel worksheet to calculate the time of flight based on the battery and the input power and the amount of amps that the individual motors would be pulling from the battery. And so the same motor could use like a 4,000 milliamp battery or a larger like 5,000 milliamp hour battery, just pulling power at different rates.
So did you use like average current draw and just like P equals IV? Okay.
Yes. And then
Um,
so we got those numbers from a very great resource, innovate.com, that had those spec sheets for each motor.
Okay. What about for like a high current condition, like where you're taking off, for example, you're generating like a lot of heat. How do you know your components aren't going to overheat in that scenario?
Right. That's a great question, a great concern. We didn't implement any max power conditions, both in our time of flight and for overheating considerations. That would be a great thing to do in the future, now that you mention it.
Okay. These are all like OTS components. Most times they're not going to blow up, but John and TA had suggested times like in his RC career in which they did. So I was wondering like, how would you check for that in the future?
So we could use sensors inside the aircraft during our first test flights to see what those max temperatures could reach. And then, of course, compare those with the maximums on the components themselves. That has some inherent risk, because if it is hotter than it should be, that we don't really want that to happen on the test flight. So for a preventative measure, we could design in some venting, which we did not include this time around because we had such a large volume inside the fuselage for that heat to dissipate. But if it was a much smaller area, then yes, some venting, or I guess fins on the outside of the aircraft to increase the surface area to dissipate that heat would be a good preventative measure.
And I think if we were truly concerned about the heat, we probably would have done a static test. But these, again, as you said, were off-the-shelf components, and we weren't really concerned about such a short flight time. 9-10 minutes probably wasn't going to be enough to cause these items to overheat.
Yeah, I'm not going to press you on it. It's really not that serious. But in the future, like analytically, it'd be nice to like look at components like that. But 10-minute flight is totally fine. Can we go to the wing loading?
Yes.
So I guess like the max, not yes. So is this like worst stall angle attack and like maximum velocity that's expected?
Yes.
Okay. Have you also considered like loading conditions like during landing, or like during like a really bad like spin out, for something example?
We did not, because it'd be really hard to calculate like a crash condition. So we just kind of hope for the best using our carbon fiber spar. And again, we had that safety factor of about a little over 3. So we thought it would be fine for that.
Okay. And does this assume like a infinitely stiff like fuselage?
I'm sorry, what was that?
Does this assume like an infinitely stiff fuselage? In most cases, your wing is probably going to be stronger than your fuselage.
Correct. It did assume that.
Okay. In reality, that's probably not the case. So a couple of recommendations is, one, like looking to like the landing scenario, because that's actually a maximum loading condition. I think Tom, the Northrop guy, grilled us on that before because we didn't consider it. And also consider your actual attachment points of the wing, because that's going to be what's reacting a lot of the load.
Okay, thank you.
Yeah. Let's talk about the carbon tube that you used as a spar. So Do you know what type of carbon tube that was, like what the layup schedule of it was?
It was a pultruded, just 0-degree fiber tube.
So unidirectional.
Yeah, unidirectional. Yeah.
Okay, so can you assume that your maximum stress is accurate for that then?
Yes, you can.
Okay, but the formula that you're using in this case is for bending stress, which is sort of an out-of-plane loading. I guess there's also tensile components to that, but I would be concerned about whether or not these calculations are accurate. I think you actually mentioned in the presentation that the tube wasn't as stiff as you guys predicted. The reason that is,
Sorry, yeah, I just want to mention that is we used two different carbon fiber components. One was the carbon fiber spar square tube, and then the other was simply a 3mm carbon fiber rod that was just used as the pivot points for the control surfaces. And that was the one that was not very stiff.
okay, understandable.
Yeah. On the 2 slides from now, the FEA confirmed that the maximum stress was actually less in the spars than the hand calculations. This shows 433. The hand calculations showed 544.
Okay. Yeah, I would just be skeptical about those hand calcs because hand calcs for a carbon fiber material is anisotropic. It may not necessarily be accurate. The FEA is a good way to confirm that, but that's only if you set up your FEA properly. So how did you set up this FEA? How did you define the material properties?
Yeah, we I used just the modulus of elasticity from the manufacturer and assumed a cantilever beam fixed at the middle of the wing. So, and we also use the actual lift distribution from XFLR5.
Which software is this?
This was SolidWorks simulation.
Okay. Yeah, SolidWorks simulation isn't really very good. I understand if you like limited on the actual software.
Yeah, I agree.
But especially again for modeling like actual anisotropic material, usually just in the case you'd want to use like something like ANSYS ACP or even CMAP, which again like kind of overkill for the scope of this project. So I'm not gonna really fully about that. But in general, like I'd be very skeptical about putting like FEA and like a structural analysis unless like you have like a ton of analysis on it. And this is the flexion of just the spar itself. Do you consider like the stiffness that the skin and the ribs add as well, or is it just the spar alone?
No, for the FEA, I just assumed the 3D printed parts weren't there. And that was kind of just a built-in factor of safety for us. We kind of knew the epoxy and 3D printed material ones are going to be like extremely strong and when it add a lot of stiffness, but it is a little factor of safety built in.
Okay, yeah, and you say that 8 centimeters is acceptable, and that's like before all the stiffness added. Again, it's fine. So just in the future, maybe just like do a bit more deeper FEA analysis. You're going to include it in a report because pretty much every design review I've ever had where I had FEA, and if it's like not like super in depth, I end up getting roasted on it. This is fine though. Okay.
Okay, thank you.
Did you have? I really liked how you guys like had a bunch of data on like selecting your battery and selecting different components. Do you have anything on like how you selected your motor and prop?
So that was with the same Excel worksheet. For brevity in the presentation, I did not include the other graphs that we use to optimize the system.
Yeah.
But is that what you're talking about?
Yeah. Was this the spreadsheet that John gave you guys?
That was the spreadsheet that he gave us was a combined parameters from, I believe, DBF, but the spreadsheet I'm talking about is something that we made ourselves that took those entries and all of those parameters and used Excel just to compare them based on the restrictions that we set. So the initial estimations didn't give us enough, I guess, hard set variables to really make an informed decision. So we set that increased flight time, we set a prop diameter so that it wasn't so arbitrary. But those decisions in and of themselves were less so requirements from the project and more so how do we just narrow down the list.
Okay, that's fair. Just for like a general presentation critique, like it'd be cool to see those like a bit more details about your powertrain selection. Because a lot of that just ties into your fundamental vehicle goals. And again, like tying back to the goals, like it'd be nice to like get more conversation all in one spot. This is just like an aesthetics thing. But if you say like early on your goals, like your thrust ratio is this, your lift to drag ratio is this, and then you can go off of those goals, select your powertrain components. That would be good for your presentation.
Of course. Thank you.
Let's talk about how the actual plane was assembled. You mentioned that fasteners failed, and when during assembly, like how did that happen? Where did those fail?
I can talk about this.
Yeah.
So the wing section ended up being completely fine. We originally intended for there to be a PLA plate in the fuselage, and it had insets for nuts to sit in. But at the time we did not have access to PLA, and we were printing on a pretty tight schedule for trying to make our first test flight. So we ended up printing that out of lightweight PLA as kind of a last ditch effort. And then those the nuts in the PLA insets immediately stripped out. So then not being able to get those fasteners back out, we decided to just glue the entire wing to the fuselage for our first test flight.
Okay, so my understanding was like the actual PLA had failed or something, like torquing too hard or whatever.
No, I'm sorry. Yeah, that was a misunderstanding.
Okay, yeah, because I was going to recommend heat set inserts. It seems like you guys already did it. So
yeah, we were thinking about heat set inserts. We ended up deciding to just try to use a little bit of super glue to keep those nuts in place, but without the PLA part, and replacing it with a lightweight PLA part just meant that the nuts really had no chance in staying directly in place.
okay, just two conceptual questions about the actual wing design. Where did you locate your spar in the wing?
That was at the quarter cord.
Okay,
Yeah, I'll
cool.
pull up that and highlight it.
Yeah. That's obviously for the maximum lift location.
Okay, the reason I'm asking is just because the group last year didn't know that. Okay, and I see your servos were also the arms are coming out the bottom of the wing. Was that intentional?
Yes.
Yes.
Okay, why is that?
Want me to explain? So for any like modifications to the airfoil, we wanted all the changes to be on the bottom of the airfoil, because the top of the airfoil is the most important part to be as smooth as possible.
Why is that?
Yeah, that because disruptions in flow on top of the airfoil cause that part to stall. And also that the air, like, to create lift, the air has to move faster over the airfoil. That's more drag if there's parts extending upwards. And also the flow below the airfoil is just pretty close to just normal ambient flow. which doesn't really affect the lift of the airplane.
You're on the right track. The key point I was trying to get to is that you have a high pressure region below the wing, which is a lot harder to disturb the actual flow of the air versus low pressure on top. You disturb that, it creates flow separation, a lot of drag. Just a conceptual question. I think your guys' landing gear design is really smart, very intuitive. Especially the second design, making it one piece and having it attached to the top of the fuselage as opposed to the bottom. So good job on that. Did you guys do any pre-flight tests before flying?
So that was more of an oversight as a relatively inexperienced pilot. I was pretty much relying on the expertise of our TA John, and there wasn't much discussion at that point when it came to pre-flight tests to conduct. Our balancing test was at least definitely ineffective at figuring out where the center of gravity was. We later dialed in that process. The only real pre-flight tests that were conducted were control surfaces deflections and whether or not they were accurately deflecting to the right extent. But other than that, it was a large oversight in the maiden flights for the lack of pre-flight inspections and testing. That was then later corrected in our other flights.
Okay.
Adding in, we did do a wingtip test to confirm the deflection of the wing, and also we tested the landing gear to see how much it deflected.
Okay, yeah, that's all great. I would like to see that in your presentation. The pre-flight tests are pretty standard for this. Is like taxi testing, CG testing, control service testing, and then also structure testing if you want time for it. What were the biggest challenges you guys faced? Is there anything that you go back and change if like from the beginning?
I think proper documentation of all of our processes. We were kind of limited in the ability for us to show exactly what we were doing in the manufacturing process. We didn't necessarily set up a proper secretarial position to document all those. And I think communication was definitely a big second one.
Yeah, again, just some advice like in a group like this, it's just some shared like place to take notes. In industry, they tend to use like Jira products like Jira, Confluence. We don't have access to that for broke. We just use OneNote and Teams. I think you guys had access to PDM this semester, which is great. We didn't have that last semester. But yeah, that's all I really got. Overall, great job, guys. Great job flying. And design, good presentation.
Thank you very much for all your questions.
Thank you.
Thank you.
Thank you so
Thanks,
much
Stephen.
for your feedback, Jacob. We really appreciate. And also, Jacob mentioned like Tom Singer, like the audience from industry. I just want to explain that because I received an email yesterday that people from industry asked like when the presentation and they want to join and everything. And then the organizer of the event is email copy to me all the time. And then the organizer of the event is saying, reply that because it didn't pay money to the department, so to decide not to invite. That's why this semester we really, I don't know this afternoon, but at least for the presentation now, why we don't have the audience from the industry. It's the department decision, so sorry about that. And also for the presentation, also the overall performance for the whole semester, I really appreciate it. Great job. And I also like your presentation and everything. Just some small comments of some small points. So start from the beginning. The project goals, page 2. Yeah, so I see the takeoff weight, wingspan, thrust weight ratio, cruise speed. Why you didn't include the wind loading?
So I can talk about that also. We decided that we didn't want to go too in depth with everything on our project goals, just for time considerations on the presentation, as well as leaving everyone having enough to talk about and explain within their own slides. In terms of aesthetics, not including too many bullet points and having too much text on the screen. We decided our project goals would be like our overall very specific, like our overall overarching goals, and the very specifics would come later. In terms of wing loading and describing all of that, we decided to leave it for their specific sections.
So I asked this question because, well, maybe different people have different opinion, but I do think wind loading is a very important as parameters in the initial estimation because it's a guidance for wind design. Otherwise, how do you know how do you want to design your wing? And also on page 8, oh, sorry, wait a second. On page 5, sorry, on page 5, it said, okay, they expect 35 Newton, 8 pounds of lift at a cruise condition. I mean, if you don't have wind loading at a different situation in the initial estimation, how do I know this 8 pounds is enough or not? So I do want to see let's say if you don't want to put at the very beginning at page 2, at least in your wing design, put at the very beginning what is target, and then talk about why you design your wing in a certain way, and then you talk about, okay, this is our design result. Is it enough or not? Does it satisfy the initial estimation or requirement? I think this is a more clear logic to do a presentation. Otherwise, I mean, there are like 1,000 ways to do a wind design. Why you choose a specific way? How do you know? How do I know it's good enough? Right? Give me an initial estimation. Give me a target. Give me an expectation, and then talk about why you design a certain way, and then talk about why your design satisfies the expectation.
Definitely understood. Thank you.
Yeah. And also on page 3. So there are very small thing. The GOE 443, GOE 433, which one is correct?
That's a very observational. Yeah, thank you for that.
And also, in general, when we show a graph, just a general recommendation, you see the 3 line of the first 3 airfoils. We prefer to use some color with strong contrast so we can really easily see like the difference of the performance of each different airfoil. Right now, the 3, well, I can tell, but it's like it's not that easy. So that's the thing I want to say, that like in your future presentation, always make sure that if you want to make a comparison of different airfoils, use color that with strong contrast. So when I see it, I know, okay, which one is which airfoil and which one performs best.
I agree. I think these were pulled directly from XFLR5, but we could have exported the data and then recreated our own graphs.
And I think that the software, it has some setting that you can change the color of each one. Yeah. So just like a general comment of this one, and also on page 5. I mean, which color represents what? It's really tiny. I think I need to spend some time to figure out which color represents what. Oh, and it's so tiny I really cannot read. I don't know.
Yeah, so it's the colors here more represent like a range of cruise speed velocities. I'm sorry if it's not very clear in the graph. We probably could have done more.
I know, Alice, I need to know clearly like which line represents what.
Okay.
Right now there's something at the corner of the graph, in top right corner of the graph, but it's just too tiny to read. And since you have some space, make it clear. So I know what I'm reading, what I'm comparing. What information do I need to get from the graph? And page 11. So I really like the trade study and everything, but the thing is that you have this trade study and you have the input, thrust, propeller, weight, time of flight, and everything, and you show the fourth one. I mean, but when I check the parameters, I mean, it doesn't seem that the one you chose, really has the best parameters for each category.
Right. I will agree. Just looking at it, it does look that way, that the fourth one appears not to be the best. For brevity in the presentation, I did not include the chart where they were normalized on a scale from 0 to 1. So each of those parameters compared against the other three. And so those scaled, added together, that fourth one ended up being the highest score.
Okay, now I understand. Because if I just read this slide, I feel confused because it doesn't seem to be the best option. And why you choose this one? Yeah, now I understand. Just make sure that it's clear in the report, because report we do need some details. I know there's some constraint for the presentation.
I think one of the major benefits of choosing that fourth design was the smaller propeller. As you can see, it's a 13-inch diameter prop.
Okay.
That did allow for us to increase our ground clearance, which happened to be a problem on our first test flight.
Okay. So probably, let's say just in terms of the presentation, you probably cannot emphasize which one is the main consideration for your decision. Because if you check the thrust, it's not bad. If you check the weight, it's not the, well, it is best. If you check the time of flight, is not. So probably you can just like emphasize, okay, the main consideration of choosing this one is because the diameter of the propeller.
Right. I will say that what's defined as best for each of these parameters, I go through them quickly. The lowest input watts got the highest score. The thrust that was closest to 96 ounces, or that 6-pound thrust weight ratio of 1-to-1, in order to optimize for it, that's what scored the highest. And then the lowest propeller diameter, and then the lowest weight and highest flight time. So the thrust, having a better thrust wasn't necessarily the highest scoring option.
I agree. I apologize. I probably said something wrong. Yes, I agree.
No, I think that this requires a little bit more explanation. You're actually absolutely correct that we should have emphasized that. So I appreciate that.
And I agree.
Yeah. So, and also for the structure analysis, actually, I think your group did in a way that is like, I'm not saying it wrong, but I think it's like different than we normally think how we normally do the structure analysis, because let's say most of the time when we say do the structure analysis, we normally say, okay, this is our design, or let's say this is the loading condition when in the extreme condition, and this is because the wing is already designed at the airfoil and everything dimension wise is designed based on the aerodynamic performance. So those things we consider it does not change. So the thing we design is, let's say we want to design the thickness of the spar or anything, and we have the stress, like what is maximum stress end up in your design, and what is yield strength or allowable strength of the material we use, and then you have safe factor. So we consider normally this is a regular way we do the structure analysis, like what is in the end is comparing the maximum stress in the structure and allowable stress of the material, and we know safety factor, and we know how safe your design is. But somehow I feel like you did in a different way, and then your calculated values include the load factor, which is a little bit like surprised me, because I feel like you calculated load factor. So I want to know the logic in this structure analysis.
Well, load factor, yes, it was calculated, right? But it was just dividing, I think, lift by weight. So I mean, it wasn't like an in-depth calculation. It was just, it's just called a calculation.
So normally what we do is that in the structure analysis, we assume based on the requirement, the performance requirement of the aircraft, we assume a reasonable load factor and put that load factor into the calculation, because you can see that on page 13, all the equation, it depends on the load factor. It should not be a calculated result. It should be the information for our calculation. And in the end, we calculate the maximum bending moment at root, we calculate the maximum normal stress caused by bending at root, and we know if our design is safe or not. But the safety factor, sorry, the load factor itself should not be a calculated results. You know what I mean?
Okay, I got you.
Yeah. So I would say that is like a more standard way to do structural analysis. Just want to make the logic very clear here. And yeah, and also I definitely agree with Jacob on the FE analysis page 17. We normally do not prefer to use SolidWorks for FE analysis. So you can use ANSYS, you can use Abacus, you can use Nastran. So use some professional FEA software because SolidWorks is really not for FEA analysis. And for the on page 25. Oh, so I use the one you uploaded yesterday. Let's see. The materials, probably the page number changed. Yeah, ASA. So this one, you said you used the ASA for wing spar?
It was ASA for the wing spar plate that holds it in the root of the wing. Not for the actual wing spar itself. Sorry, that looks confusing now that you mentioned it.
Because I remember you guys use a carbon fiber tube for the
Yeah, sorry about that.
Okay.
Thank you.
Yeah.
If you go back to the wing CAD, you can actually see the plate we're talking about from an internal view. That might be helpful as well, but thank you for that tip.
Yeah.
And I do want to apologize for the page numbers changing. We did eliminate one of the tail slides just because we felt it wasn't okay. Thank you.
Because last night I need to download everything because this morning I went to the a meeting this morning at 7 and came back just right before your presentation. So I need to make sure that everything downloaded before I sleep last night. So that's why I used the slides last night, but it's fine. No worries. And I think overall great job, and I really appreciate hard work this semester and the test flight and everything. And okay, I want to explain that 2 points off is because you guys fly without landing gear. So I hope you can understand.
That's completely understandable.
Because well, so I hope that is okay. And oh, one thing I want to ask, did you guys finish the class evaluation?
Yes.
So because I check online, the response rate is still lower than 50%. So
It's definitely not group 4. Group
Yeah,
4 got their
we
course
did it.
evaluations done.
thank you so much. I really appreciate that. So just in case if anybody has not been submitted, please submit it today because I think today's deadline, right?
Yes.
Yeah, and because this two in the past semester, well, last semester Jacob was there. We only had 2 groups. This semester we have 4 groups. I think this class is still, it's like more like test run, and I still have a lot to learn. Well, right now I'm kind of depend on the TAs because the whole thing is new to me. So I need to know like the direction, which part I should work on, and how to make this class better. And also, I think your feedback would be very important for me to make this class better for the future students. So I would really appreciate if everybody can submit that class evaluation. So I know how to change. And so that's all my comments. Is there any other comment from Jacob?
No, I'm all good.
Okay, thank you. So so the rest work is final report. So great job, and just focus on your final report and everything should be fine. Thank you
very much.
Thank you very much.
Thank you.
Thank you.